Let's take a look at lesson 1.2.7. It says, what if you've got a helium balloon that has a volume of 20 liters at sea level? So here's our balloon at sea level. What do you think will happen to this balloon if it rises into the sky where the temperature is colder? So let's think about this. If the temperature goes down, we've learned that the volume of the balloon should go down as well, because as the temperature goes down, the particles slow down. So if they're colliding with the walls of the balloon at a slower, decreased rate, the balloon is going to shrink. However, it also says the pressure is going to go down at that higher altitude. If there are less particles surrounding the balloon, like here there's a lot of particles pushing on the outside as particles push back, but at that higher altitude, now there's less particles outside and the same amount inside, so they're going to be able to push and cause the volume to grow. So we have two competing factors here. One tells us that the balloon should shrink, and the other one tells us that the balloon should grow. So this is where math is going to come into play so that we can actually figure out which one wins. There will be a link that you should click on so that you can actually see what happened with the bell jar experiment. But what you're supposed to do is predict what will happen to marshmallows and a balloon if we create this tiny little atmosphere where we can actually remove the gas particles. We create almost a vacuum. There's still a few gas particles. It's not perfect, but there are much fewer gas particles. So what's going to happen to something that's in there if you remove the gas particles? So actually click over on that YouTube, pause this video, watch it after you've made your prediction, write down your observations, and then let's talk about it. When there's less pressure, actually let's talk first, when there's normal pressure inside and you've got this marshmallow, there's air particles inside the marshmallow too, so they're pushing out, but these particles outside are also pushing on the outside of the marshmallow. If we take away the particles inside, or many of them, now the particles inside the marshmallow are like, woo! We can push out and the marshmallow will expand. It's like there's nothing holding it back. So the marshmallow will grow. Same thing with a balloon. And this matches with Boyle's law, which we've already talked about with the syringe experiment. As the pressure, or as the volume decreases, the pressure will go up because there is less space for the particles to move around. And vice versa, as the volume goes up, the pressure will go down. And in order to make this equation work, you need the temperature to stay the same and the number of gas particles. Those things need to be constant. And so you can see with the syringe, you're assuming that you're doing this at room temperature, and we're never changing how many gas particles are inside. So what if you've got to do a math problem? Let's see how we can use this equation, it says, to predict what will happen with the gas. What if you've got a 2-liter container? I want to remind you that liters are a measurement of volume. And it says the pressure is 1.5 atmospheres. That's another unit for pressure. What will the new pressure be if the volume goes up to 4.5 liters? Well, we should plan on the pressure going down, because if the particles have more space to move around, now they're not going to be colliding as frequently with the sides of their container. Let's look at the step-by-step process that we want you to use when you're solving problems like this. Number 1, always write out the equation that you're using. So here we did P1 times V1 equals P2 times V2. Then we plug in the numbers that we know. So this problem told us a 2-liter container, that's volume 1. It told us the first pressure was 1.5, and it told us the new volume was 4.5. So you can see in number 2 here, I rewrote those. Step 3 is show your work to divide both sides by a number in order to isolate the unknown variable. Our unknown variable is P2. We don't know the new pressure. But if I divide both sides by 4.5, notice with my yellow marker here, I slashed out the 4.5, and on this side, liters canceled out, leaving me with 1 unit left, which makes sense because we want a pressure, so atmospheres can be our units for that. Then in my calculator, I'm going to type 1.5 times 2 divided by 4.5. My new pressure is 0.67 atm. Number 5 says be sure to label your units and box your final answer. And then think about your answer. Does it make sense? So in this example I wrote, this makes sense because as the volume went up, the pressure went down. The particles now have more space to move around and collide less, decreasing the pressure. So now it's your turn. Pause this video and see if you can do this whole process of writing out the formula and following those 6 steps. Let's do this. So again, the formula is P1 times V1 equals P2 times V2, and then we plug in what we know. It says that we have an initial volume of 5.6 liters, and we know it's at a pressure of 1 atm. We don't know the new pressure, but we know the new volume is 2.8 liters. So I need to try to get P2 by itself, and this 2.8 liters is bugging it. So I'm going to divide both sides by 2.8 liters. Now, what's canceling out here is handy to point out because we've got the 2.8, 2.8, and then liters and liters. So in my calculator, I'm going to go ahead and type in, this is step 1, step 2, step 3. In my calculator, 1 times 5.6 divided by 2.8. That comes out to be 2, and the only units left are atm. So I'm going to box my answer for number 5. Step 6 is think about it. Does it make sense? Yes, this makes sense. As the volume went from 5.6 down to 2.8, the pressure went up from 1 atm to 2 atm. And this is because now the particles have less space to move around, so they're going to be colliding more frequently, creating more force. How about another one? It's got volume and pressure, a new pressure, and we want to know the new volume this time. Step 1, start by writing my equation. Step 2, plug in the numbers that I know. It says the first pressure is 0.02 atm at a volume of 400 liters. The new pressure is 1 atm, so what volume must have caused that? I need to divide both sides by 1 atm to isolate my V2. That is going to cancel out. ATM is going to cancel out so that I'm actually left with liters. That was step 3. Step 4 is punch this into your calculator. 0.02 times 400 divided by the 1 on the bottom. That comes out to be 8 liters because those are the units left over. Does this make sense? Yes, this makes sense. In order for the pressure to increase, the volume must have decreased. And it did, because the pressure went up from 0.02 to 1, and the volume went down from 400 all the way to 8. Again, pause this video so that you can make a prediction about what will happen to a balloon if it's been blown up in a hot flask and then set into a bucket of ice water. Just to set the scene for you a little bit more, you've got this balloon on the top of this flask. It's got just a little bit of water to make sure we don't break the glass, but these are really hot particles. And then what's going to happen when you put this into a bucket of ice cubes? And then watch that video so you can see what happened. And then let's talk about it. So the balloon actually goes down into the flask. And that's because now these particles inside the flask are moving so slowly that it's a decreased pressure. And so as the temperature went down, the pressure went down as well. And so now there's more pressure outside pushing that balloon in. So the volume of the balloon went way down. So as the temperature goes down, so does the volume of that balloon. So this mathematical relationship is called Charles' law. You can see it says as the volume goes up, this is a direct relationship, the temperature must also go up at a proportional rate. But in order for this equation to work, pressure must stay the same. And we'll talk about that. It was a little bit interesting with that demonstration because it's hard to sometimes control the pressure. And also the number of particles must stay the same. All right, so what if you've got a 2-liter balloon at 293 Kelvin and all of a sudden you take it outside and the temperature is now 263 Kelvin. So you're assuming that the pressure is the same because you're not going to the top of a mountain or something. It's just colder outside. It's pretty relatively the same, we should say. So how are we going to solve this? Well, our new equation is V1 over T1 equals V2 over T2. So first focus just on the blue writing in number 2. We set this up, 2 liters at 293 Kelvin is equal to an unknown volume, but the temperature went down to 263. So what we need to do to solve for this and get V2 by itself is we need to multiply both sides by 263 because that will get rid of it from the bottom here. So if we multiply both sides by 263, you can see I slashed out with the yellow here, the 263 and the 263. And now on the left side, the Kelvin units are canceled out. So we're going to do 263 times 2 divided by 293 in our calculator. And we're going to get that new volume of 1.8 liters. So does this answer make sense? Well, yes, because the temperature went down, and so that would slow down the particles inside the balloon. So in order to keep the pressure constant, the volume would also need to go down. And it did. So as the temperature went from 293 down to 263, the volume went down from 2 liters to just 1.8 liters. So let's try this with a couple more